Okay, welcome back, geographers. So the topic for this video is what I did live on the other day, and it is going to be one of the most useful videos for you, particularly in terms of the synoptic elements of A-level geography and your ability to apply this content here to papers 1, 2 and 3. So what we're going to be covering is the unbalanced carbon cycle. So firstly we're going to cover what do we mean by the carbon cycle being unbalanced. Then we're going to see what the impacts are on the water cycle. Following that, we're then going to look at the unbalanced carbon cycle in the oceans, and then finally we're going to relate it to the terrestrial biosphere. Not sure what happened with the line there. Let's crack on. Your ability to do well in the carbon cycle fundamentally boils down to your understanding of the carbon cycle as one big system. And it operates within a system of what's called dynamic equilibrium. Within this equilibrium, we have both inputs and outputs of carbon from the various stores. So again, fundamental to doing well, or fundamental to understanding this, is having that knowledge of the stores. What do we mean by inputs? What do we mean by outputs? So for example, there may be inputs to the atmosphere, which might involve outputs from the oceans. So again, it's more just kind of terminology that we're dealing with here. We've got inputs and outputs within a system that operates within a dynamic equilibrium. So what we mean by balanced carbon cycle are natural background levels, i.e. volumes of carbon that we would expect in certain stores naturally, and then inputs and outputs from to those stores that are in line with natural background levels. So naturally, what we mean by an unbalanced carbon cycle is when we've got increases or decreases in inputs, or increases or decreases in outputs that are above or below natural background levels. There's something that we've done that's kind of tipped the balance in a certain way. So what we're going to look at first is how we've managed to do that. Okay, there's two ways that we can think about that unbalancing. We can think about it both directly and indirectly unbalancing. The way that you want to think about direct unbalancing of the carbon cycle is predominantly with land use change. So what that might mean is something like deforestation. We've cleared some forested area to make way for agricultural land, or to make way for an urban settlement. So that is a direct change. What we're doing there is there's decreased inputs into biomass, and therefore there's then increased inputs into atmosphere, yes, or there's decreased outputs from the atmosphere to biomass, yeah. So we're thinking about this in terms of inputs and outputs. The other way is this indirect. The main thing that you want to think about with the indirect unbalancing of the carbon cycle is it's the combustion of fossil fuels. You mainly want to be concerned with this CO2. So carbon dioxide, in terms of the levels of greenhouse gases that are above natural background levels, this constitutes around 89% of those additional greenhouse gases. So they are the most significant contributor to what we term today as the enhanced greenhouse effect. So we're going to be predominantly looking at the indirect unbalancing of the carbon cycle, and that's because there's increased inputs of carbon dioxide, greenhouse gas, into the atmosphere store. So very important there. Now it's really important that you don't confuse the greenhouse effect with the enhanced greenhouse effect. Greenhouse effect is natural. This is the thing that warms the planet. It keeps the average temperature of the globe around 15 degrees C, which means that the globe can sustain life. If it were any cooler, or if we go into ice ages, less life can be sustained. What we're currently dealing with is the enhanced greenhouse effect. So what that means is there's increased greenhouse gases moving into the atmosphere, which has increased this greenhouse effect, which means we're getting an increase in this average temperature, and that has a bunch of knock-on effects on the remainder of the carbon cycle. Let's look at how that works. Okay, so the sun's incoming rays, shortwave UV radiation. A certain percentage of that is reflected by clouds and aerosols in the atmosphere. So that's around 30% is reflected back out into space. The remainder makes its way down to Earth and can be absorbed by the land and the sea. When it's absorbed, it's then re-radiated as long-wave infrared radiation. This is then absorbed by the greenhouse gases in the atmosphere. And it's not just CO2, so it can be CO2, which is 0.04% of the atmosphere. There's also methane, water as well, which is a greenhouse gas. And these all absorb long-wave infrared radiation and trap that heat in the atmosphere, or more specifically the troposphere, and that then creates the temperature that we have currently. So what happens happens when we increase that greenhouse gas concentration is that we trap an increasing amount of that long wave infrared radiation and the temperature goes up. So not only do we have more of these greenhouse gases in the atmosphere that will have some kind of impact, we also have raising temperatures because of this mechanism here. So what does that then mean for our stores? Well, we're not going to get to the stores just yet, but first we'll look at what's the impact on the water cycle. Easiest impact to talk about is what's happening along the ITCZ. Well, as we know, insolation is most concentrated along this line here, which is around 5 degrees north, 5 degrees south latitude. So because this is taking place, what that means is there's the highest degree of evapotranspiration. And if you remember, this kickstarts the creation of the Hadley cell. So then air moves laterally and it descends along this area here. The same in the southern hemisphere as well. So between these latitudes here, this is where we have descending air and high pressure. We'll come back to those areas afterwards. So what we have in this area here is a high concentration of convectional rainfall. So we get high rainfall here anyway. Now when we increase the enhanced greenhouse effect, we have warming of the atmosphere. So what that means is evapotranspiration increases. It also means that the atmosphere holds more moisture. Crucial statistic for you here is that with every 1 degree increase, that equals 7% more moisture in the atmosphere. So it's significant. So what's going to happen along here is we'll get increasing floods. And that's because there's an increased volume and intensity of rainfall, which increases the likelihood of saturated overland flow, or even just overland flow. Rivers start to flood, and then we get more flood events. Now we can come back to what kind of an impact that has on the terrestrial biosphere when we cover the terrestrial biosphere in a bit. Now it's not only along this area here, or between 5 degrees north and south of the equator, that this is going to impact certain places. If you remember, the Earth has an axial tilt. So what that means is the concentration of solar radiation moves north and south as the Earth orbits around the Sun throughout the 365-day rotation. So in the northern hemisphere, in summer, insolation actually concentrates to a higher degree up here, and if you remember, that brings with it the monsoon rainfalls. So it's not only along this area here, along the equator, there'll also be an increased intensity of monsoon rainfalls as well. That will not only have implications for rivers and floods and natural processes, it's also going to have implications for people. So there's going to be more death, there's going to be more destruction of crops, there's going to be more, well, anything that you can think of that flooding impacts. Next up, what's going to happen here around 30 degrees latitude? Because we've got warming atmosphere, and again, that gives this area here, the ITCZ, a stronger force, a stronger convection, more energy. If there's more energy going this way, there'll then be more energy going this way as well. And that extends this cell laterally, and that's what's happening. There is this expansion of the Hadley cell, and it's varying. It's around 1 to 2 degrees latitude north and south. So what's the significance of that? Well, the significance of that is when we have descending air, we have high pressure. Now that descending air, that's always been descending. That's nothing to do with anthropogenic influence on the climate. This is where we have things like the Sahara Desert, and we have areas such as Saudi Arabia and Iran, the Middle East, the arid regions anyway. But what's happening here is that high pressure zone is extending increasingly north and south. So there's areas of southern Europe that when the ITCZ moves north, and so too do the cells and the northern extent of these cells, areas like Greece, they're increasingly experiencing very high pressure areas. So it's thought that Greece will suffer from a decrease of around 20 to 30% in their summer rains, and that's just one area. So whereas there's flooding here and in your monsoon regions, what we're going to get in southern Europe is increasing drought. And that's the thing with the unbalanced carbon cycle. Wet areas become wetter, dry areas become drier. The next impact we can't escape talking about is the impact on the cryosphere. The water isn't just stored in liquid form, it's not just stored in gaseous form, it's also stored in solid form in the form of ice, and that is the cryosphere store. So essentially what's happening with a warming atmosphere is that there's increased thawing. Now initially that will create an increase in meltwaters, and what that could do is it could increase flood flood risk, and maybe in the short term it might actually increase water availability in certain regions. But then over time this ice store is going to shrink in size year on year, and what that means then is that there's going to be, yes, decreased flood risk over time, maybe over the longer term, but it's going to increase the risk of hydrological drought. And then it becomes really interesting because your cryosphere store, remember the color of this is going to be white. When you've got a white surface, that increases the albedo of the Earth's surface. So what do we mean by albedo? Albedo is essentially the ability of a surface to reflect incoming solar radiation. So if we've got a white surface, incoming solar radiation simply boom, bounces off it. There's no absorption and therefore no re-radiation as long-wave infrared radiation. So there's no warming effect. But then with thawing, and then the colour change that comes alongside thawing, so maybe it's in the permafrost region and it's now turned to a dark brown surface, there's increased absorption and therefore increased warming. Now what we can talk about there, and we can bring in this fundamentally important concept when we're talking about dynamic equilibrium, is that we create a positive feedback mechanism. It's essentially warming leading to more warming. So that's fundamentally important when we're talking about the cryosphere store in the water cycle. Next up is the oceans, okay? Now with the oceans, what we can bring in is both increased CO2 concentrations in the atmosphere, and we can also bring in warming. Both of these things will affect the ocean store. So initially, if you remember, with increased CO2 into the atmosphere, what that does is it increases the diffusion of CO2 into the surface ocean store. Now what that does, it creates an excess of hydrogen ions, or more hydrogen ions than is usually created in natural background levels. As you know from the slow geological cycle, there's that release of carbonate into the ocean store from chemical weathering, and these carbonates can be used by the marine calcifiers and coral as well. So these hydrogen ions react with the carbonate ions and these will form carbonic acid. So the more of this that is created, the greater the degree of ocean acidification. So this is one of the most worrying parts about the increase in CO2 in the atmosphere. We've unbalanced the carbon cycle by releasing CO2 into the atmosphere, and what that's doing is it's acidifying the oceans. The oceans are alkaline, so naturally they'd be around a pH of 8.2. Currently they're around 8.1, and it's thought that by 2100 they will be around 7.9. So why is this worrying? All ecosystems have evolved to exist within certain environmental conditions. So if we change the acidity, that changes the survival rate of many of the organisms. Coral, for example, start growing at around pH 7.7. That's bad. We'll come on to that. In addition to this, the increased acidification is also causing erosion of the shells, so that protection mechanism. In addition to that, with more hydrogen ions taking the carbonates away from being used by these marine calcifiers, that decreases the availability of carbonates. So all in all, what's the effect of this? Well, weaker shells, increased predation, and decreased biodiversity in the marine store. That's going to mess up all of your food webs, all of your food systems, all of your food chains. Not to mention the fact that if coral die, increasing amounts of coral die, they're home to 25% of marine species. So ocean acidification is not a good thing for all of these reasons here. It's really going to mess with the carbonate pump. It's really going to mess with the biological pump as well, if you think that these are living things. In addition to this, ocean acidification also impacts these little creatures here that, if you remember, these are our phytoplankton. Phytoplankton require certain nutrients in order to develop. What acidification does is it reduces the bioavailability of iron, so their ability to utilize iron in the oceans to develop. So we may even get less development of phytoplankton. So with ocean acidification causing a decrease in phytoplankton and a decrease in coral, overall that's going to result in decreasing photosynthesis. Now, once you can get to this point in the unbalanced carbon cycle, you're onto a winner, because you can always then talk about a positive feedback mechanism. With decreasing photosynthesis, that's increasing CO2 in the atmosphere, which causes all of this, which then again leads to a decrease in photosynthesis. So we have that positive feedback mechanism. So always look out for your opportunity, particularly when you're talking about systems and systems theory, for talking about positive feedback mechanisms. It's again this idea of a tipping point. We've upset the balance, and because we've upset the balance, that's further contributing to an upsetting of the balance of the carbon cycle. Okay, so what about warming? The main impact that you should link warming to is this: coral bleaching. So what is coral bleaching? When it gets too warm, coral eject what are called Zooxanthellae. Now these zooxanthellae, they exist on the coral, but they photosynthesize on behalf of the coral. It's a symbiotic relationship. It's biological mutualism, if you like. Yes, you can live on the coral, but you have to photosynthesize on their behalf. So they contribute to coral growth through photosynthesis. So when this starts to happen, that's when you see large coral ecosystems turning completely white, because these are the things that will give them their colour. They're a sort of colourful bacteria. And once again, because they photosynthesize, we're looking at another positive feedback mechanism there as well. The other thing to remember with warming as well is that there will be an increase in the thawing of land ice. This is really important. You've got to say land ice. If you say an increased thawing of sea ice, doesn't necessarily have the same impact as saying land ice. Now with land ice, what that will do is it will increase the amount of fresh water entering salt water at the poles, and we'll come on to why that's significant in a second. In addition to this, obviously, there is warming of the waters. I'm going to take you back to something I spoke about in the last video, which was the difference between the poles and the tropics. So remember, difference in temperature, the difference in salinity is what drives this, the thermohaline circulation. And remember, this is the thing that takes carbon from the surface ocean store, takes it to the deep ocean store where it's got longer residence times. It's also the thing that cycles nutrients and carbon dioxide right to the surface, which can be utilized by the base of our biological pump. So not only are we messing with coral, not only are we messing with other marine calcifiers, we're also messing with the thermohaline circulation, which has an impact on the entire ocean ecosystem. So the unbalancing of the carbon cycle probably has the most significant impacts at the global scale on the ocean store. And then finally, we have the impacts on the terrestrial biosphere. So from this side, moving towards this side, we're transitioning from balance to imbalance and the impacts. As you can see, on this side, we have two of our really important carbon sinks. One, we've got wetland, and two, we've got forest ecosystems. In a healthy forest, remember, forests can generate their own rainfall by biotic pumping. Evapotranspiration, that creates low pressure, draws in warm coastal air, contains large volumes of moisture, and that contributes to the creation of its own rainfall. This is particularly true in the Amazon, which at any time can generate anything between 30 to 60% of its own rainfall. Wetland areas, remember, these are a fantastic carbon sink, and that is because there is the slow decomposition of organic matter down here, because there is an anaerobic environment, and that's what creates very fertile peat deposits. So as we move over to here, what's going to be occurring that is linked inextricably to the water cycle. So you can't talk about the impacts on the terrestrial biosphere without making reference to the water cycle. So this is why it's so important that as you're revising the carbon cycle, you're also revising the water cycle alongside it, because there are those interlinkages at all points. Okay, the first thing, so if we talk first about the impacts of drought. Drought, remember, in southern Europe, we've already seen this, there's increasing wildfires. This is a very rapid release of CO2 into the atmosphere, and the reason that there's increased wildfires is because there's less moisture, and that means that there's plenty of what's called kindling being produced, which is dead organic matter that's dried out, which catches very easily and allows those wildfires to spread. So wildfires, again, something that's unbalancing the carbon cycle and creating one of those positive feedback mechanisms. The other thing as well is this idea of forest stress and forest dieback. Trees need water to grow. That doesn't mean that they won't grow without water for a time. They will still grow, but it'll be a weaker form of growth. That means they're less resistant to pests and pathogens, and therefore dieback will take place. With forest dieback, obviously, once again, we have a negative feedback mechanism because that process of photosynthesis is simply not happening. Then we've also got to bring in the fact that there's going to be increased floods. So with decreased forest cover and increased floods, that increases overland flow because there's no interception from vegetation, and then we have loss of soil. So areas are becoming less able to recover after these drought periods. Furthermore, we've also got the thawing of permafrost. This is a real worry because a lot of carbon is held in the permafrost. So if you remember, because the temperatures are so low, there's a lot of organic matter contained within these soils. And then once they start to thaw out, what that does is it increases the rate of microbial decay, increasing the rate of respiration, and we have an increased release of CO2. In addition to this, there's also, because there's gas pockets of methane, the increasing methane. And the worry with methane is that it is 25 times more potent than CO2 as a greenhouse gas. So the more of that we enter into the atmosphere, the worse the enhanced greenhouse effect is going to get. And then finally, we've obviously got the drying out of wetlands. They cease to become wetlands, they are just then big areas of unprotected soil. And that again will increase decomposition rates because there's the increased exposure to oxygen. So that's it. So that's the unbalanced carbon cycle, bringing together all of the concepts within inquiry question 1 about how the cycles work, but thinking about if we tip that balance, inputs, outputs, we upset the dynamic equilibrium, it will have knock-on effects on the water, oceans, and terrestrial biosphere. Next video I'm going to be doing is how you can use all this stuff, or the entirety of the stuff in inquiry question 1 in exam style questions, and that's where you're really going to get the benefit. It's no longer just content, it's kind of content and how do I formulate this into a paragraph that's going to score me high mark. Okay, so I'll see you then.